Hello, so this video looks at the electron configuration of transition metal atoms and ions. Okay, now the transition metals are that section of the periodic table in the middle in the D block, and this is because we will be filling the D subshell with electrons as we move across the periodic table. So D block transition metals are metals with an incomplete D subshell in at least one of their ions. That is the definition of a transition metal. Just like with the other electron configurations we've done with the other elements, you add electrons in order of energy. You start with the lowest energy. So the first transition metal is scandium, and it has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. Okay, notice that there are 2 electrons in the 4s subshell because it has a lower energy than the 3d subshell. Now, there are different ways of writing this. Some people prefer to put 4s before 3d, and other people show the 3d before the 4s. Either of those is correct, as long as you've got the right number of electrons in both. So what's an important bit to remember is that the 4s subshell is filled before the 3d. And the reason is because it's slightly lower in energy. So nothing has changed since we looked at that in the previous lesson. So as I said, you can either do 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2, or 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Both spectroscopic electron configurations are correct. So it follows the Aufbau principle. Now, as with chemistry, as you will learn, there are always exceptions to the rule. The 2 exceptions in this case are chromium and copper atoms. If you have a look at a chromium electron arrangement, what you would think it would have would be 1s2, 2s2, 2p6, 3s2, 3p6, and it would look as though it should be 4s2, 3d4. However, instead, the actual arrangement becomes 1s2, 2s2, 2p6, 3s2, 3p6, and then it has 3d5, 4s1. And the reason it does this is because you get a special stability associated with the D subshell being half filled. So instead of having 2 electrons in the 4s subshell and 4 in the 3d, one of those 4s electrons moves to the 3d subshell so that you've got 5 electrons and you get that special stability. A similar thing happens with copper. Copper could be 4s2, 3d9, but instead is actually 4s1, 3d10, so that you've got a completely filled 3d subshell. So watch out for those when you are filling out your electron configuration tables. So just like before, this one is very difficult to fill in your notes, so a separate sheet has been created. You should complete the spectroscopic notation and the orbital box notation. I've shortened these a bit so that you can use the noble gas arrangement, so we're only looking at the 3d and the 4s subshells for entering the electrons. Okay, so those are the electron arrangements for the first row of the transition metals. Like I say, for advanced higher chemistry, you only need to be able to give the electron arrangements for the first 36 elements. Okay, now one thing you'll remember, probably even maybe from 3rd or 4th year, is that the transition metals have variable valencies. They can change their valency. And this is because they can lose the 4s electrons, and they can lose some or all of the 3d electrons. So they can lose a variety of number of electrons, and this gives them different valencies. Always, it's the 4s electrons that are lost first. Okay, and that doesn't matter, including copper and chromium, it's still the 4s electrons that are lost first, rather than the 3d electrons. So for example, an iron atom is 3d6, 4s2, and for an iron 2 ion, it would just be 3d6. Some people write 4s0, it's fine to do that. Okay, just remember that there will be, for the iron 2 ion, there's no 4s electrons. In your orbital box notation, you would just leave the 4s subshell empty. So transition metals as we said before, are defined as metals which have an incomplete D subshell in at least one of their ions. There are two exceptions to this, or two metals that don't conform to this rule. Zinc and scandium. You may remember from National 5, zinc always has a valency of 2, so it always forms a 2+ ion. So the electron arrangement of a zinc 2+ ion is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. So it does not have an incomplete D subshell in its ion. It has a full D subshell. The same with scandium. If you look at that, so scandium forms a 3+ ion, and it has an electron arrangement of 1s2, 2s2, 2p6, 3s2, 3p6, and it has no 3d electrons and no 4s electrons. Okay, so actually, in fact, zinc and scandium are not considered transition metals, and they don't always behave in the same way as transition metals, as we will see later on. So you have an activity again, a separate sheet has been created for you to complete the electron configuration of the ions. And then can you have a look at the electron configurations of the ion 2 and the ion 3 ions, okay? Looking at the spectroscopic and the orbital box notations, and use these to explain why ion 3 compounds are more stable than ion 2 compounds. Once you've completed this, there's questions 37 to 41 to complete, and also an associated check test. Any questions, please just